Okay, I think we have 46 people so far, and I'm going to introduce Professor Agrawal, and then we will start the talk 10 minutes after the hour. Okay, and so good afternoon, good morning, good evening, wherever you are. So today it's our great pleasure and honor to invite Professor Agrawal to our PIC seminar series. This is also our first virtual talk, so hopefully we will go through that without any glitch. Now, Professor Agrawal needs no introduction. He is a household name in the photonics community. Many of us have benefited from the textbooks he wrote. I, for one, used his nonlinear fiber optics textbook when I was a grad student. And even today, I often need to refer to this book during my research. This is an older edition. I loaned my newer edition to my grad students because they're using it. I also use this as a reference book in my grad course, ultra-fast optics grad course. His other well-known textbooks are Optical Communication Systems and Applications of Nonlinear Fiber Optics and Light Propagation in Gain Media. So you can see that he's a prolific author, having published 450 research papers and 8 books. In fact, there is a new book coming out this year, Theoretical Foundations of Nanoscale Quantum Devices. So I'm looking forward to reading this one. Now, needless to say, Professor Agrawal is an expert on nonlinear optics, silicon photonics, and optical communications. He received his MS and PhD degrees from the India Institute of Technology, New Delhi, in 1971 and 1974, respectively. Now, after holding positions at the École Polytechnique, France, the City University of New York, and AT&T Bell Laboratories, Dr. Agrawal joined in 1989 the faculty of the Institute of Optics at University of Rochester, where he is currently James C. Wyant Professor of Optics. Professor Agrawal is a fellow of IEEE and OSA, the Optical Society, and a Life Fellow of the Optical Society of India. He's also a member of European Physical Society. He's a recipient of many prestigious awards for both his research and teaching contributions. For example, in 2012, IEEE Photonics Society honored him with its Quantum Electronics Award. In 2013, he received the Riker University Award for Excellence in Graduate Teaching. Professor Agrawal was given the Asher-Hoffman-Beller Medal in 2015 for his outstanding contributions to education in optical science and engineering. He was the recipient of 2 major awards last year, Max Born Award of the Optical Society and Quantum Electronics Prize of the European Physics Society. Now, as a recipient of so many prestigious international awards, both in teaching and research, Professor Agrawal is an inspirational role model for us all indeed. So today we're excited to be here to learn from his latest research on space-time duality. It's a fascinating concept, and I'm looking forward to this talk because I know this is going to be a real treat. So please join me here virtually in welcoming Professor Agrawal.
Thank you, Lee, for such a generous introduction. So the title of my talk, as you see is written here, Space-Time Duality in Optics and its Applications. So it may sound a little strange kind of title because it looks like an almost philosophical topic, but I will explain to you what I mean by that in a minute. So let me start with a historical introduction, because that I think will give you some idea where things started. So in the 60s, 2 people, one in France and one in Russia, noticed what we call now space-time duality. But there was just a mention, they didn't do much with that. Then in 1989, a Canadian group, actually some of you may know the Najarthi and Kolner, these people introduced the concept of temporal imaging and a time lens. So that was actually the first time the concept of time lens was talked about. And I will spend some time on that today. And then more recently, people have been focusing on, this is our work on temporal waveguiding and ultra-fast time holography and some telecommunication applications. I will mention about that too. Imaging is also another place. And as a reference for you, there was a tutorial in Advanced in Optical Photonics in 2013 on this topic. That's quite useful for anyone who's interested in optical signal processing. So with that, let me go to my main thing. First thing I want to tell you, what is space-time duality? Well, what do I mean by that? And in fact, it's a very simple idea. The idea is the diffraction of beams in space. Everybody knows the beams spread as they propagate. So that's diffraction. And similarly, you can think about pulses, which are confined in time. When they go inside a dispersive medium, they start to broaden. So we know those two things. But then if you look at them mathematically, you find that diffraction, for example, is governed by this paradoxical equation. So this equation here, as you see, is showing you is how the diffraction is governed. So there is a single parameter here called this K, which is propagation constant related to wavelength. The wavelength of the light is telling us how the beam will spread, essentially. And that's the paradoxical wave equation. Now, if you do the similar thing for the pulses, and you consider the propagation of pulses in a dispersive medium, and dispersive medium could be just an optical fiber, could be a waveguide, silicon waveguide, or any kind of thing. All kind of media exhibit dispersion. Then in that case, this equation you get looks like that. Where A is always this amplitude of the electric field, if you want. And so you notice here that this equation looks pretty similar to this equation, except you notice there is sign change. And the parameter which comes here is we call beta 2. This is known as a dispersion parameter. And for any medium we are talking about that, this is a known parameter. It's called beta 2 because the second derivative of the propagation constant with respect to frequency. That's the definition of this parameter. But so you will see this parameter will come a lot as we proceed further. So keep in mind the notation here is called beta 2. So notice that beta 2 turns out can be positive or negative, while K is always positive, of course. So when beta 2 is negative, these two equations become almost same. But when beta 2 is positive, then the sign change. But that doesn't change too much. In either ways, the main point is that anything you can do in space, you should be able to do in time, and vice versa. And that's why it is called space-time duality. So for example, in space, we know a lens can focus a beam, and lens you can use to make images. So we can do something similar in time. We should be able to focus a pulse with a time lens, for example, and we can also be able to make some kind of time microscope, which is an imaging system. That was the basic idea in this case. So let's continue with that and ask ourselves, what is the idea behind time lens? What is a time lens? So let's look into, first of all, a normal lens. So here's my normal lens. If a wide beam comes in, when it passes through the lens, as we know, it gets focused down. So it comes to a focus at the focal point, right? So the focal length is an important parameter for a lens, for example. So you ask the question, well, what is happening to the electric field that is passing through this lens? And the answer to that is given in this equation, which tells you essentially, as my input goes through the lens, and the output is wavefront is curved. And so it's a curved wavefront. So that means for different x, I get different phases. So phase depends on position, where you are in the beam position. And focal length comes here, over here. So that's all the lens is doing actually. Everything you know about the lens is coming from this wavefront curvature, curving the wavefront. So we can say if I can make a time lens, it should do the same thing in time. So I can rewrite this in time now. So I say in time, it should do something like this. In other words, I have a same quadratic form here, and then I have a parameter here, df, which is equivalent of the focal length if you want. But of course, units are different here. This is in the time square if you want to make the unit less. So different units, but it's same thing, same idea. So if I can have anything which can look like the phase looks like that, then that's a time length. So the question then becomes, how can we get this kind of phase? How do we get that? So let's look at the next slide into that. So here is one way of doing it, and that's what I discussed a long time ago, that if I use a phase modulator, that can act as a time lens. So phase modulator is a time lens. So here I have my modulator. Modulator is made of electro-optic material, and I can apply a sinusoidal voltage to this. Over here, this sinusoidal voltage will change the phase because change the refractive index, the phase will change. So if there's an electric field coming in here, and the output is phase will change, it will look like something like that. So this is what this is doing. Okay. Now mathematically, if you want to write this down mathematically, you will say this modulator is multiplying the phase in this fashion: phi 0 cosine omega mt. So omega m is the modulation frequency, phi 0 is some kind of phase shift, and this is the sinusoidal modulation, like a sinusoidal function. So at this point, this does not look like what we want. However, you're dealing with a short pulse, and that short pulse is centered in the center here, somewhere, something like this, in the center of this thing here. Then around here, this is a parabola. So I can expand this cosine in a Taylor series, and I can write down the cosine in this form. And now, if you see it right away, that for the short pulse, which is within this modulus cycle fitting in there, if I have a phase which is quadratic in time, this is sometimes called chirping. Basically, your electro-optic material is chirping the pulse. Sometimes you can say that. So essentially, I'm getting a phase shift which is quadratic done by this modulator. And hence, this is a time lens. I can use a modulator as a time lens. Now, there are other ways you can do this too. So let's look into some other ways you can get this kind of effect. And this is discussed here. So first of all, techniques for making a time lens. There is anytime you get a quadratic phase shift, which is equivalent to linear frequency chirp, you have a time lens. So what we want the frequency changing linearly with time. And so this is how the frequency is behaving. And so any technique that can impose a linear chirp on a pulse can be used to make a time lens. So right away, you can think of many nonlinear techniques that provide a linear frequency chirp. For example, cross-phase modulation by a parabolic pump pulse inside an optical fiber would give you a quadratic phase, a linear chirp. Even a Gaussian pulse in the normal dispersion region of a fiber produces a linear chirp through nonlinear effects. This is called optical wave breaking in the case of fibers. And finally, Fourier mixing inside a silicon waveguide or an optical fiber can also be produced a chirp on the pulse. In this case, you have to chirp the pump pulse, and the chirp of the pump pulse is transferred to the signal pulse to get it chirp the way you want, essentially. So those are the ideas people have used. A lot of people use silicon waveguides or fibers to make these time lenses using nonlinear effects in this case. But a modulator, you can think of it like a linear effect if you want. They're not really using nonlinear in that case. Okay. All right, so let's look at some of the things we can do now. Now that we know how to make a time lens, we can start asking ourselves, what can you do with a time lens? And so first of all, we can say, well, we know in space we can focus a beam. That means I can create a narrower beam starting with a big side beam. That means I should be able to do a compression, a pulse compression. So what I can do, so I can come with a wide pulse, a long pulse over here. So this is my long pulse over here. And then I put a time lens. So this is, I'm putting this element here. Now this is a modulator if you want. I put a time lens. So after this time lens, I get a pulse, which is still long, but it's chirped now. This time lens is chirping the pulse. And then the propagation in space here is equivalent to propagation in dispersive medium. So I use a piece of fiber. So this could be just a long piece of fiber. So this fiber will provide a dispersion to this pulse, and in the process it will compress the pulse. Just like here it is becoming narrower, this pulse it will focus the pulse basically. So you can compress a pulse, and this is very well known by the way. This is known that if you chirp the pulse somehow, non-linearly or linearly, then going through a dispersive medium, you can compress the pulse. And this is a short pulse you can make. So this is like a focusing by a time lens. Very simple thing. Okay. So what else you can do? Well, next thing you can do, you can make a imaging system. Just like in space, you can have a lens, and you can put an object at one end, and you can put an image at the other end, you can make an image. Now I can do the same thing here. I can put a time lens over here. This is my time lens. And then I have an object here. This is my object. The object is some kind of pulse train, some time-dependent function. That's my object. And now I put a piece of fiber here. So this fiber is basically my object side fiber. and then I have a fiber on this side if you want. So I can take a modulator and attach a fiber on both sides. If I choose the length of these fibers right, I should be able to image this pulse. So I can stretch it or compress it. You can do either way, but this is like an imaging system. I can image it. And if you turn out to go through the math of this, you find that the imaging condition is exactly what you find from the space. Like 1 over u plus 1 over v equal to 1 over f is now that condition comes through these d parameters. So these are the d's, 1, d2 are the related to fiber dispersion. And this df, which is the focal length for the lens, depends on the parameters of the modulator, essentially, in this case, how it will do. So there's a condition that you can satisfy, and that will create an imaging. So you can magnify this signal by a factor of 10 or 100 if you want. Now you might say, well, why would I like to do that? And people like short pulses. Why would you get a broader signal? And by the way, this does not distort the pulse. It just simply magnifies everything by that factor. So the reason you would like to do that, because short pulses, if they have some funny shape, are very hard to measure. There is no, a femtosecond pulse, you can't measure the shape very well, what's going on. I mean, autocorrelation does not give you shape of the pulse. So you may simply use an imaging system like this with a time lens to stretch the pulse by a factor of 10 or 100. And now a femtosecond pulse is now in picosecond. And now you can use simply a detector and you can measure it. If you know the scale factor, you immediately know what the pulse looks like, original pulse looks like. So this is very good for measuring short pulses. You can use this idea to measure short pulses. That's advantage to that. Okay, so that's one application. Of course, this you can also make a temporal microscope, which is same thing. Same microscope imaging system. A microscope sometimes can reverse the image and magnify the image. So this is an example where you have an object here, and this object is being magnified over here, and the process is inverted. So you can do the same thing. You can have a time lens here, over here. Then you have a fiber over this side, a fiber on this side, and now you can do the imaging. And if you did that, then this pulse, my signal will stretch, because that's a magnification, and also will reverse, invert. Notice that this is mirror image. So that's because your inverted image, I'm inverting in time. So this is a mirror image of this signal here. And the magnification factor is exactly what you expect in space. In space, you expect this magnification factor to be depends on the distances here. And here, this depends on the dispersion of this medium and dispersion of that medium. So everything in space follows in time. Everything you can do there comes to exactly the same thing. And that's what we mean by space-time duality, that you can do almost everything in space in time and vice versa, by the way. All right, so now I want to show you something where you don't even need a time lens. So you ask yourself, do I really always need a time lens? Can I do something without a time lens? And the one thing you can do, you can create a temporal Fourier transform using simply a piece of fiber. So so basic idea, again, very well known in optics. If you know, you probably know from diffraction theory that if you take a slit and this slit output is diffracted and you're far enough, you are in the what you call far field, a far field diffraction, then the shape of this distribution you get here is the Fourier transform of the slit of this field here is known. In other words, I'm creating a Fourier transform, optical Fourier transform, you want optically, by simply propagating through in space. So that means now I can take a long piece of fiber and satisfy my far field condition, which is a very simple condition. Then I can send a pulse with some spectrum. And on the output end here, my shape of the pulse will mimic the spectrum, will become exactly like the spectrum, right? So in fact, I created a spectrum. So I can now measure this pulse on oscilloscope, and that is like I measure the spectrum, if you want. There is a conversion factor, which you can find from theory, which tells you exactly you can measure the spectrum. Now you might say, well, what's the benefit? Why do I measure spectrum like this? So I can measure spectrum using a OSA, optical spectrum analyzer, right? What is the benefit? Benefit is the single shot. You're getting the entire spectrum right away. In a case of OSA, has to average over a long time. So you can never get a spectrum of a single pulse. Now you might say, well, why is it interesting? Well, imagine that there's a spectrum that changes rapidly with time. And you want to measure those spectral changes from pulse to pulse. Something is changing every time. How do you measure those changes? It's very hard to do. But this, a piece of fiber makes it a very nice way to measure the spectrum in real time. So you can measure the change in the spectrum in a picosecond time scale or nanosecond time scale taking place without needing any spectrometer if you want. So this is a very popular technique. It's called a dispersive Fourier transform. People call sometimes a dispersive Fourier transform. And all you need is a piece of fiber. Just you need a little, just a dispersive medium. So let me show you, I will talk more about that. Now the other thing you can do, let me go back here talk about something. Now this is not a true Fourier transform. Why is that? Because the spectrum does not change. The spectrum does not take the shape of the pulse. You know the spectrum cannot change in a linear medium. The spectrum doesn't change, but the shape changes and becomes a spectrum. Now if you want to do a true Fourier transform, what do you do? Well, you can do that by using what is known as a 2F or 4F processor. This is a very well-known thing in optics. So for example, you can take a lens in spatial optics, take a lens, and if you put something at one focal point, the second focal point is the Fourier transform of that. And this is a true Fourier transform. It changes both x and k, if you want, in this case. And so in this case, you could then simply, let me just stop this. So in this case, once you get the Fourier transform here, you can now do a processing. You can put here, you can modify the spectrum if you want by using a faceplate or by using apertures. You can modify the spectrum, and then you can recreate the Fourier transform back again in space. And this is what people say to do processing. This is a optical signal processing technique. So you can say, well, okay, if I can do this here, I can do same thing in time, except that I need 2 time lenses and I will need a lot of dispersive parts, but it will exactly do the same thing. So this is one way to do a optical signal processing of pulses. Now, here is something wonderful here. In fact, you don't need to do all this complicated thing. You can simply take 2 pieces of fibers and do the same thing. So remember, I just showed you a minute ago that if you can take a long piece of fiber, then this long piece of fiber, whatever pulse you put here, you can a Fourier transform here, right? We just talked about that. So now I can do my processing here. I can modify the spectrum here, and then I put another piece of fiber, but with a negative dispersion. And I can go back to a time domain here, and I will do the same thing as there. The only reason why I can do this so simply rather than doing this complicated fashion is because I can change the sign of this beta 2 parameter. Remember, in the case of space, my diffraction, I cannot do negative diffraction. I can only do one kind of diffraction. But dispersion can be positive or negative. And that's why I can simplify this big picture by just 2 pieces of fibers. But I needed 2 different pieces, one with positive dispersion, one with negative dispersion. So that's something you can do. So that's very useful also. Okay, so let me show you this, why people are excited about it. So a dispersive Fourier transform basically says I can use a long piece of dispersive medium. It's a long fiber, for example. It's a long fiber. If I send a pulse through this, then what comes at the output is a Fourier transform. Basically spectrum. Whatever spectrum this pulse had, I see this in time, I see the spectral shape. And this is a diagram showing you how what is happening inside the fiber is basically chirping the pulse. As you chirp the pulse, you spread it out, you chirp it, and the process, the shape of this spectrum, shape of this pulse mimics the spectrum, essentially. So now you can measure the spectrum by just measuring this pulse itself. So that's what it does. So as I already mentioned, this is known as a DFT. Sometimes people call it time stress transform. It creates a single shot spectrum and allows to study spectral change in real time. That is what is useful. And that we can use it for medical imaging, for example, or sensing. Lots of things, when things are changing with time, you can use it for that purpose. So let me give an example of that. So we have this up here. So here's an example of that. So let's say I want to make I want to image something. This is my sample. I want to image this in some way. How would I do that? So let's say I send a short pulse through this sample. This short pulse is very wide spectrum. So wide spectrum and short pulse. I send it through the sample. Now, a sample, different molecules will absorb different wavelengths, right? So after you pass through the sample, my spectrum will be modified. And these absorption tells you where the molecule was, because it takes time for pulse to go through. So different location of this thing is telling me which molecule was where, essentially, if you want. So there's an image of the sample is stored here in the spectrum. So now if I take a dispersive element, as anything, then I can make the shape in time mimic that spectrum. And now I can put a photodiode and measure the spectrum. The next pulse, if this thing changes, if this thing moves, next pulse which comes in will change the spectrum differently. I will see from pulse to pulse changes in the spectrum I can record, and that will tell me what is happening in real time. How this sample or molecules are rotating or changing, you can figure that out. So this is very useful. This little thing is extremely useful for that cell. The other application, for example, of the same thing would be that you can use a spectral filter to make pulses of arbitrary shapes. Suppose somebody says, I want a certain shape for the pulse. So you can take the shape and make a Fourier transform. You take the shape, and now you find a filter that will create the spectrum of that shape. So here's what I did. I filter, and this filter modifies the spectrum into this shape. And now I want this shape to transfer to time. So I use a piece of fiber, and I get the same shape in time. In other words, I can create any shape I want by using a suitable spectral filter. I can make any pulse shape I want. So you can see these are very interesting and very useful things as such. This is, I think these are the applications for telecom. So I won't spend too much time on it, but essentially, as I told you, that we can do a Fourier mixing inside a nonlinear medium, and that Fourier mixing with two pieces of dispersive fibers can be used to make a true Fourier transform. That what I mean by that, whatever is in the time, the pulse shape mimics the spectrum, and the spectrum it mimics the time. In other words, there's a conversion in both space and time both. This is different than simply using one piece of fiber. So with that, people say, oh, I see. So that way I can do something telecom, which is very important for them. I can have a WDM signal and convert to time division multiplexing. So for a wavelength division multiplexing, I can go to time domain and create time domain signal, or vice versa. And so, people have done that in the lab. I want no time to explain to you details of all of that, but I can show you a little bit. So here is one example. This top figure is showing you how it is done. There was chirp pump pulses. So this is time here and a frequency there. But main point is the following, that on the left side here, I have a time domain signal. It's a multiplex in time. So it's OTDM, what we call that, and 160 gigabit signal. So this is a one wavelength if you want, but it's an OTDM. Now I do this for my time length, and I'm using chirp pulses. From my pump pulses are chirp. So because of that, I can actually create a spectrum here now on this side. This is my idler spectrum, which now has multiple peaks, which are like WDM channels, which contain the same data, but now it has been in wavelength. So what was multiplex in time is now multiplex in wavelength. And that's essentially what you would like to do for some application. Or you can go reverse way if you want to do. And this is another experiment where we have a starting on this side with a WDM signal, 32 channels. And then we use this time length idea to convert into a single broadband, which is multiplex in time essentially. So I'm taking a WDM signal and convert it into a very high speed OTDM signal in this case. So these are very interesting applications for telecom. So I think, I hope I have given you an idea that this timeless concept is very powerful, has a lot of applications. So now I want to move to something that we have been doing in my group. So this is, so we asked a very simple question about 5 years ago. We asked that we know what the reflection and refraction is. So if you have a spatial boundary, and this is what you see here, there's a spatial boundary. Think of it like the air, the glass on this side. And if a beam comes in, then we know it gets reflected and refracted. These are the Snell's law and all that. This is known in space. We know that. So we ask, what is the temporal analog of these things? Can I do a temporal reflection in time, right? Now, of course, you have to understand the language here. I'm not going to do reflection like you see here. Image will not be there. Image will be very different looking. It's something different. Now, how do you understand them? How do I understand? How would I do this? What would I mean? So let's think of this here. What is happening here is, if you think of this, that I have a spatial boundary. That means at the spatial boundary, I am suddenly breaking here. Things are different on this side and that side. That means I have actually broken the space invariance. And if you broke this, so my momentum cannot be conserved. You know, quantum mechanics, if you have a space symmetry, we break, the momentum cannot be conserved. And if you break the temporal symmetry, then the frequency will not be conserved. So in this case, at a spatial boundary, frequency is preserved, but momentum can change. So photons momentum change, but frequency is same. So light frequency doesn't change, but momentum changes because direction changes. Direction is related to momentum. If you want, k vector direction is a different momentum. So in a spatial boundary, we preserve the frequency, but change the momentum. That means the temporal boundary is the opposite. I have to preserve the momentum of photons, but frequency can change. So I expect that in my temporal reflection, the spectrum will change. I want spectrum to change. So when I say temporal reflection, I'm not really thinking of this image. What I'm saying is a pulse will approach this boundary, and then as it crosses this boundary, part of the pulse spectrum will change. So it will split into two parts. One part spectrum will be shifted such that it will never cross the boundary. It will stay on the same side, and the other one will go to the other side. So I want to see some kind of this kind of effect. So remember this point: a change in angle at a spatial interface translates to a change in the frequency of incident light. That's the most important thing here. All right, so let's think about what we can do with that. All right, so it's the same idea, same thing I'm showing you. In space, your angle change. In time, my frequencies will change. Incident frequency will become a reflected frequency and transmitted frequency. And we have to make sure that the vector is conserved, that the momentum is conserved when this happens. Okay. So that's very simple. So now it turns out that it turns out we have to assume a moving boundary. A static boundary is very hard to do. So we are thinking a boundary that is moving. And as it's moving, the refractive index across the boundary is different. The refractive is on the other side. So in a moving boundary, this is how the refractive index will change. But if I now work in a moving frame, the boundary becomes stationary. And hence I expect in a moving frame, boundary is stationary. And so here is the real picture. Nothing is moving backward. But in a moving frame, this will reflect and this will transmit. So be careful. When I say moving frame, when I see reflection, nothing is going backward. A pulse is coming in, it just start moving slowly. So it never crosses the medium, it stays on this side, but it's still moving forward. And this will speeds up, this one slows down. And so that's what we expect to happen. So but in the moving frame, you will see exactly what reflection and refraction looks like. Let me show you now how we get that. Okay, so we thought let's try to understand this. How can we make a model for this idea? So here's the idea, that if there's a temporal boundary, we discontinue that boundary. So then we expect my dispersion relation. So beta is a function of frequency. I can expand into a Taylor series. I get a quadratic term here. This is my beta 2. And this delta beta 1 gives me relative speed of the pulse with respect to temporal boundary. This is my delta beta 1. Here is the relative speed of the pulse because it has to approach the boundary. And so this is what I get before the boundary. But after the boundary, so this is a Heaviside function. After the boundary, I change refractive index. So I add a little, I increase my beta by beta b, because I'm changing refractive index on the other side of the boundary. So refractive index are different on the two sides. So this is a dispersion relation before and after. So there's somewhere there's a boundary and the refractive index is changing on the other side of the boundary. So the question becomes, how do I include that mathematically to see that? And we were able to do that very simply by writing an equation which you might have seen very often. So this is the pulse propagation equation. And this is very well known, this is the equation. Generally you have a 0 here on this side. But what I do now, I put here a Heaviside step function such that for t less than tb, this is 0. But for t greater than TB, this is 1. I'm increasing my refractive index by a small amount on this side. So this equation now can include the boundary effects in this fashion. And now we can go to computer, solve it for some pulse. So we take a Gaussian pulse. It's a bits, we took 1 picosecond here, and we assume the boundary is located at 5 picoseconds. So the parameters we are assuming is that this is the how the pulse is moving through the medium. This is the dispersion parameter, and this is the change we are making. Now, how big this change is, refractive index? Remember, beta B is K0 times delta M. And K0 is very large. So this the refractive index we are changing is 1 part in a million, 10⁻⁶ or something like that. Very small change. So this is what we solve this on a computer. Oh, here actually, the number is right here. And if we have the 1 micron refractive index by 2 times -7. So we solve that on a computer, and we try to see what we get. And the results are on the next page. Let me show you that. That's what we get. It looks exactly like reflection and refraction now. It's the same picture. So here is my pulse initially. So this is the distance, and the pulse here is right here in time. And this pulse is approaching the boundary. Here's the boundary here. So you can see that this is the boundary here, right here. So the pulse is approaching the boundary, hits the boundary somewhere around here. And as it hits it, you can see immediately some of the pulse energy comes back here. That means pulses start moving slower. And it will move slower because the spectrum has changed. And that you notice here. This is input spectrum of the pulse right here. And at this point where they hit, I have created a part of the energy has come over here. And so there's a shift, big shift for the reflected wave, and a small shift for the refracted wave. But there's a spectral shift for both of them. And so this one is the reflected and it's coming out here. And this is refracted. So this is exactly reflection, but now in time, right? As we said that. But notice that nothing is moving backward. Everything is forward. Keep in mind that. It's important to know. Okay, so we said, okay, can we look at into a spectrogram? Sometimes it's nicer to look at spectrogram. So we're looking at a spectrogram means I'm plotting the time and frequency on the same diagram. So at the input end, I plot the pulse spectrum is over here. So this is in the x direction, here is the pulse spectrum. In the time direction, this shape. So this is becoming like a bullet, if you want. Shape and the spectrum both are here, given here. This is what you call a spectrogram. And now I start moving towards the boundary. So this bullet is moving towards the boundary, moving again, and now it's hitting the boundary. And so it's starting to cross the other side, and it's going to cross the other side. You can see what happens. Right away, it starts radiating something on this side, and after it crosses out, it starts going over here, and then something is coming out here. So this is a motion of this pulse hitting the boundary, and then leaving the boundary the other side, but the process creating a reflected signal over here. So the same thing. It just shows a different way of looking at the same picture we showed you before. Okay, so now we ask ourselves, is it possible to calculate what these frequency shifts are, how big they are, and can we calculate them? So we did that by making a very simple diagram because we want to conserve the momentum, right? So I'm plotting this my parabolic curve. This is my dispersion curve, parabolic that we assume. So this is before the boundary is this. And after the boundary, I change the refractive index, it just goes up, basically. So green curve is after the boundary and blue curve is before the boundary. These are the dispersion curve. And now I have a pulse with some spectrum. So this is my spectrum of the input pulse. And then, so you can extend the spectrum over here, go up. And then you ask yourself that if I want to conserve the momentum, then I have to always stay on this line over here if you want. Same momentum. For every one I have to preserve the momentum. If you just impose that condition, you will find that immediately that after you hit the pulse, you will get a spectrum of a reflected wave will be shifted by about 6 terahertz in this case, from here to here. But the refracted pulse spectrum will be shifted by around here, by a little bit over here. And that's the picture you get, that a spectral shift will take place because I have to conserve the momentum in this case. So that is the picture. And mathematics is very simple, actually, with that. So I will show you the next page. And then, so what you find is you start with this momentum equation, and you ask yourself, how would I, so I can say for let's take one component, omega equal to omega 0, we need to make the beta equal to beta 0, so I get this equation. So reflected pulse is confined to region T less than TB, so this is not there. So I get a quadratic equation, I can solve this equation, and I find the frequency here. So this tells you how much shift you get. The shift is negative in this case. If these are positive, shift is negative, but it could be both. It could be, if beta 2 is negative, the shift will be plus here, right? It could be red shift or blue shift. And shift depends on the dispersion in the medium, and also what is the relative speed of the pulse with respect to boundary. So these two things are telling me how much shift I get. So you can calculate the shift here. Then we said, okay, what about the transmitted one? So transmitted one, we got the spectrum again by doing the same math. We found what the transmitted one spectrum looks like, and so this is what we get here for transmitted spectrum over here. So we have an analytical expression. Now the question we can ask is that is there anything like a total reflection? In other words, is it possible that nothing will be transmitted, everything will be reflected, right? That's the next question you can ask. And you can see that it's possible because this quantity here, if this becomes negative, this quantity, then my frequency becomes complex. And there's no such thing complex frequency. So I can get a total interference condition right here, from here. If this thing over here becomes larger than 1, then I will not have any solution for the transmitted frequency, and everything will be reflected. So this gives me a total reflection condition, and I want to focus on that. Okay, so that's what I'm doing here. So total reflection is possible. And we know in the spatial case, you have to have a beam has to enter from the high index side to low index side, or delta n must be negative for that. Now, and this comes from Snell's law. In the case of temporal TIR, of course, it's a related frequency shift. And as we said, we can find from here, if this thing becomes larger than 1, then, so if this condition is true, then I should get total reflection. Now, what is interesting here is that you can get this whether your delta n is positive or negative, because if your beta 2 changes sign, then you can see that here. This is what matters. This must be positive. If beta 2 is positive, the beta v must be positive. Beta 2 is negative, the beta b must be positive. So one is the positive index, one negative index. So you just use the different dispersion parameter of different sign, but in both cases you can get total reflection in this case. Okay, so let me show you what it looks like. So this is our simulation for that my beam is coming in, it's the boundary, and everything comes to here, nothing goes to the other side. And the spectral domain, my beam shifts over here, but nothing is coming here, everything is reflected, total reflection. How much index change I had across the boundary? Answer is 10 minus 6. So I'm not changing index by large amount. I can still get this effect. Entire percentage gets reflected at the temporal boundary, and the spectrum shifts towards the red side if delta n is positive. If delta n is negative, it will shift to the blue side in that case. So this is total reflection. That's very nice. Okay, here is something else that you notice here, that when it's reflected, you start seeing these fringes here. And these fringes you are seeing is simply because the frequency of the incident wave and reflected wave are different. So they will interfere. These two frequency components interfere, you get temporal fringes. So you're seeing these fringes also. Also notice on this side, we create a evanescent wave that decays into this side, which is we expect to total reflection. And so that is exactly the same thing what we expect in space, that there is a surface wave over here, if you want, but it is a surface in time some way. But this is what is happening. Basically, you see a evanescent wave forming that you expect in that case. So everything what you have know in sort of time, in space happens in time. And this is a spectrogram of the same thing, total reflection. My pulse comes in, hits the boundary, and everything is transferred very quickly from here to here. And it never crosses the medium. It starts going back to the other side, back here. So that's total reflection. Okay. All right, so finally, I think we thought about something you might be thinking, that dispersion, when I write a parabola, I'm making an assumption. Assumption is the higher order dispersion, what we call third order dispersion, is negligible. That may not be the case. Generally, the dispersion curves can be quite complicated, and you may have a higher order dispersion. So if your dispersion curve is not a parabola, but it's cubic, then the cubic looks like something like this. The cubic equation has a solution looks like something like that. So this is before the boundary, after the boundary you change it. And now you ask yourself how many solutions there are. And you find there can be multiple solutions. So in this case, we found examples where you can create two reflected waves and one reflected. So like a double reflection, double reflection. And in some cases, you get two reflection and one reflection. So in other words, you can get multiple reflection and refraction if you include the third order dispersive effect. So that's an interesting kind of thing. That is something like that can happen. That's quite interesting. We published this work in IEEE JQ. Final topic for today is the temporal waveguide. So of course, once you have total interreflection, you start thinking right away, what about if I have two temporal boundaries separated by certain things? I mean, otherwise I can say that I have a temporal boundary here and temporal boundary here. And so refractive index, I'm taking an example, but refractive index is lower inside this, in this range here. Remember, in the case of a spatial case, your waveguide central core have a higher index to make a waveguide. But in our case, it can be higher or lower because beta 2 can be positive or negative. So we can even make a temporal waveguide even when my index across the boundary is actually lower. And that's what I'm taking an example here. So both are possible. So we just need the two temporal boundaries. Two temporal boundaries are needed. The refractive index in the central region can be lower or higher. Right? So what is the advantage of this? Basically, I can put a pulse here in the center. I can, let me draw this. Maybe I put a pulse here in the middle. And this is my a boundary here, a boundary here. So this pulse, let's say, moving toward this side. So it will hit this pulse and get reflected. And then when it comes here, it will hit here again, reflected again. So I can kind of create I push it back towards the center from each side, and hence it will confine to this window, whatever window I'm creating. So that's the idea we are trying to pursue and see whether it does or not. Okay. So first of all, we found that maybe there's something like called temporal modes of a waveguide. I mean, if we have a time waveguide, maybe there are modes of this waveguide. Turns out that is true. We actually could found everything about this. If we knew the structure, we found that we can find all the modes of waveguide. So in this paper, we have found the modes. We found this B parameter, which people do normally to talk about that. Okay. So you see this is B parameter defined like that. So you can define a B parameter, and depending on how much B is, you get 1 mode or 2 mode or 10 modes. And this is an example of those. I'm showing you a few modes here, 3 modes of the waveguide, what these modes are. So there's a model picture that you can use to understand this waveguide if you want to. That's one thing we found. And here is the actual computer simulation to show you how the waveguide works. So I'm trying to make it a single mode waveguide. And so my waveguide here is 10 picosecond wide, essentially. This is my window. And I'm putting a 2.5 picosecond Gaussian pulse here. So of course, I'm not doing very good matching. I'm not coming with the right. So this waveguide is single mode, supports a single mode. And I'm coming with not with the right kind of right width of the pulse. So what is happening is it's trying to adjust, but it's losing a lot of energy. And so it gets confined, but in the process, it loses a lot of energy. This is like coupling. I am mismatching coupling, is not coupling. So if I increase the pulse width to 5 picoseconds, so it fills nicely in this area, now you can see there's almost no loss. My pulse remains confined to the waveguide. So it's basically, you expect some sort of coupling issue. If you don't couple the input into the waveguide correctly, you expect something will happen. This is what is happening here. But clearly, you can make a single mode waveguide and can couple into it quite efficiently. And this is the idea I already mentioned that we can put we can just put a short pulse here. And this is my waveguide boundary. This is my waveguide in this width. And then pulse will go toward this side, hits this here. And because it hits, it gets totally reflected, and the spectrum will shift. So you see it shifts from here to here. Now it goes to the other side, hits this boundary, and it gets reflected again. And now the spectrum goes back to what it was before. So essentially, every time you hit the boundary, you shift the spectrum and come back, shift the spectrum, come back, and you create this zigzag pattern. And this keeps the pulse inside. So in this case, it's a multi-mode waveguide. That's what is happening. Before I was showing a single mode waveguide, it's a multi-mode waveguide. So in this case, I can simply confine this pulse inside the window by zigzagging pattern. So that's something you can see very nicely here. So having done all this, we ask ourselves, how would we do in the lab this kind of stuff? And that's what we are in the process of doing it. So if you want to make a waveguide, so we need two moving boundaries, and there are two ways you can do this. Okay. The one way you can use a microwave signal, then you can apply to electro-optic modulator. So it's like a traveling wave electro-optic modulator. And so wherever this microwave signal is, refractive index will change. So there's certain, so I can use a time window. My voltage pulse will tell me what window is, over which the refractive index will be higher inside that window. And now I can have a short pulse, optical pulse, which will, of course, travel at different speed because the refractive index is different in microwave than an optical frequency. So their speeds are not matched. So this pulse will hit boundary and get reflected and so on. So I should be able to do it by using a modulator, which I drive as a traveling wave modulator. Problem with this approach, of course, is, which we have to figure it out exactly how to do it, that the length of the modulator is not very long. When you buy them in the market, they're a few centimeters long, 5 to 6 or 10 centimeters long. So we have to do everything within that distance. And so that is this issue here, that the medium is not long enough in this case. So the second way we can do it, we can use a crosswise modulation inside a nonlinear waveguide, which could be fiber, for example. And then we can set an intense pump pulse. So this pump pulse, if I take a wide pump pulse, it will again create a window where the refractive index is larger because it's nonlinear medium. So if I use a set of pump pulse, then my Kerr effect will increase the index only when the pulse is present. So I can create a window of higher refractive index inside the fiber. And now I can send a probe, I can keep a probe inside it, and this probe will hit the boundaries, it will never leave, essentially. I can confine that. So that's another way of doing it. Use a crosswise modulation, basically pump probe experiment, essentially. And so that explains to you, so the question here becomes that I don't want my window to change with time, with length. So spreading of the pump pulse should be controlled. I can do that by choosing pump wavelengths at the zero dispersible wavelength of the fiber. If I choose my wavelength correctly, then my pump will not spread. And hence my window will be fixed. It will not be spreading or widening and things like that. So we did a numerical simulation to see whether this works or not. And I will show you this in the next slide. So here is what we did. So here is, let me explain this diagram. This is a little nicer. So this is my pump pulse. Okay. I'm taking a very wide, 40 picosecond wide, super Gaussian, basically it means rectangular pulse, pump pulse. And I'm putting it exactly the zero wavelength. So it doesn't spread. It just keeps going. It basically, it provides me a fixed temporal boundary. And now I can, for example, if I come from outside, this probe pulse is coming, hitting this boundary and getting reflected. And you can see that spectrum is changing. So this is an example of the reflection at the interface and showing you what's going on here. Now, of course, this is different than what I showed you before because this change is not instantaneous. My super Gaussian pump pulse still has some slope. It doesn't go right away up. So because of that, my behavior is a little different, but it happens. And now here's another example where I have a pump pulse, but now it's dispersion anomalous. So it's going as a higher order soliton, sub-soliton. And again, I'm hitting at that and coming back. So essentially showing you, I can get a reflection very easily by using this. So the question is, can I get the waveguide? That's the question now. So let's look at the next one. This is again reflection and refraction. There's many examples of that. So I will go to the next one even now. So here is what I want to show you. So in this case, we want to show you this, what I sort of argued before, that I can have a pump. So this is my pump pulse. So I have a broad square pump pulse. And in the center of this, I put a probe pulse. Okay. And so it's 20 picosecond by pump pulse with 10 watt peak power, and beta do 0 for this. So this is sort of a 0 dispersion wavelength. Now 8 picosecond by probe pulse with 3 nanometer wavelength shift, so I have different wavelength, and beta 2 was -10 for that. So now what will happen? This pulse, of course, will travel differently. So it start moving towards the boundary. It hits the boundary, and spectrum changes. And this is what shows you here. The spectrum shifts, it comes over here. And then it gets reflected, hits here, comes back, and so on. So this is a picture basically. So it's showing you that the probe will remain confined to this pump window. It can never leave this my pump pulse. It's trapped inside the pump pulse for that region. So in principle, it is possible to get this kind of behavior into that. So that was good to see. Here is single mode waveguide idea. Again, same thing. Only thing I'm doing now, my pump pulse and probe pulse are roughly same width. So now my pump pulse is 10 picosecond, probe is 8 picosecond, different shape. And then you can see that this is like a probe is still confined to this, not leaking. Very nicely, pump and probe is still confined there. So it's again, it's possible to have a single mode waveguide kind of scenario. So that also works. So I think I'm coming to an end here. And so let me conclude my talk, and I will take some questions after that. So what I've shown you here, the space-time duality is a simple concept, very simple idea, but it has lots of applications. And I told you about time length, and this time length can be used for temporal imaging or for making time microscopes. And I showed you that these are very powerful because you can create Fourier transform optically, and this Fourier transform can be used for imaging objects, all kinds of applications, tons of applications for this. And then second part of the talk, I told you about a temporal equivalent total interreflection for optical pulses at a moving temporal boundary. And I told you that in the case of time, frequency shift plays the role of angles. That's very important to realize that. But this has to do with the space and time. Space leads to momentum. Space relates to momentum, and time relates to frequency. In quantum mechanics, as you know, it's a delta x, delta p greater than h bar, and delta t and delta e greater than h bar. They are conjugate variables, basically. Time and frequency are conjugate variables. That's why we have that. And so we have identified conditions under which an optical pulse can be confined to a temporal waveguide. Most of the such waveguides were found analytically. Single mode condition we found. And we also showed that pump probe configuration can be used to make such waveguides through cross-field modulation. So at this point, we're in the process of doing the experiments using the cross-field modulation idea. We're still exploring the idea of this modulator idea that we can do something based on that also. Those are the experiments we are in the process of doing these days. So okay, keep an eye on that. Okay, so with that, let me stop here and let me take any question you might have.
Thank you very much. I'm clapping on behalf of everyone.
Yeah. Thank you so much. I'd like to just suggest, since we do have a pretty large audience, that people submit questions via the chat, and then we could read them out just because we have a lot of people here. That might be easiest.
Yeah, so if you have questions, please type in the chat.
So let me take a chat my screen also, so I can see that.
And usually it will take some time
Okay.
for people to type in, and maybe in the meantime I could ask a question.
Sure.
Where people think about what people are typing in. It's really good. As I said, it's a fascinating topic. So I have a question for the time lens, where you could basically do imaging and also do a magnification of a short pulse.
Right.
So in that case, it's the intensity profile that is being magnified or shrunk.
Right.
I'm wondering whether this technique can be used also to get some information about the phase underneath, the carrier underneath the
right.
intensity profile.
Mm-hmm, mm-hmm. Yeah, that is hard because the dispersive medium always changes the phase in a funny way. I mean, kind of. So when you go from let's say pulse shape changes to mimic the spectrum, right? What is happening, of course, is there's a dispersive medium is putting a spectral phase, right? I mean, it's putting a spectral phase, and that spectral phase is what distorting the pulse shape and make it mimic the spectral shape. So the phase of the chirping and the phase of the pulse are clearly being affected as such. And of course, because of chirping, the different part of the pulse have different frequency. I mean, it's not the same one frequency. In the input, you may have one frequency, but in the output end, you have a chirping. So I think the phase information is hard to extract. So this may not work very well for coherent system, for example, where things are, you have information, the phase, that might be messed up with this kind of thing. I mean, I've not seen anybody really doing the phase yet, trying to preserve the phase with that. That may be harder to do, I think.
I see. Yeah, because then it will be really interesting, right? You can just do single shot.
Right. Yeah, so that is, I think, the most important application is that you can make a single shot spectral measurement, and you can see the change in the spectrum from shot to shot, which is a very hard thing to do using a spectrometer. You can't do that, but this allows you that, and so that's what people has a lot of advantage of that. That's a very hot topic, essentially.
Yeah.
I see there's a question from Reja Rafi. Thanks for the talk. Is it practical to implement optical filters using the temporal Fourier processor? If not, what are the limitations? Okay. So optical filters, that means you are trying to have a Fourier processor, and you want to make an optical filter. So generally, you use optical filters in the Fourier plane. When you have a Fourier processor, in the center of that, you have a Fourier plane where you're converting the time to frequency, essentially. So what you're seeing is the spectrum. And people use filtering there, some kind of filters they put there to modify the spectrum, which then gets converted to time domain to get whatever shape you want, kind of. So I don't think you can make a filter with this because we are only using the either time length, which creates a which changes the phase, or we are using the dispersive medium, which also affects the phase. So I guess my short answer is the following: that there is a phase that if you go through a dispersive medium, you have a dispersive medium acts like a filter, optical filter. But this filter phase, it is not a very good filter for applications, because this is a filter which is purely has a transfer function is a quadratic phase in frequency, a quadratic phase shift in frequency, and its amplitude is almost constant in that case. So I think the filter you get using a dispersive medium is not a kind of filter you are thinking, I think. So that may be a limitation for this, because the dispersive medium acts as a filter, but this filter is like a brick wall filter, but with some phase changes. So phase function is more important than amplitude in this case. So that will be my answer.
Oh, I also have a question from Professor Mojahadi, but I think he sent it privately to me. It says, can you speak about the limitation of paraxial approximation, neglecting the polarization and the fact that there is an approximation? How these limitations shows up in the case of your temporal dispersion analysis?
Right. So okay, that's a very good point. I mean, everything here is based on the paraxial equation in space, and then we are trying to use that in time. And in time also, I'm making several approximations. For example, I'm limiting myself to second order dispersion and not including higher order dispersion. And so that leads to, in real practice, that might lead to some distortions. And that is certainly true. So this is done in a certain approximation. So question then becomes that if you didn't make those approximations, as you said, suppose you don't make the parallax approximation, then what does the dispersion equation looks like? So if you keep the second derivative with respect to distance, if you keep it there, then you can write a non-parallaxal equation. And then you ask yourself, in time, can I get something similar? That kind of thing. I don't think we have looked into that much into that. And so I will not be able to give you a very definite answer. And there's also this question of polarization, which is also very interesting. In the case of spatial case, reflection depends on the polarization. You have S and P polarization, have different reflection coefficients. And we are totally not looking at and I don't know what the equivalent of that in time is. In fact, I'm not able to understand how can I get this polarization dependence in time. So that's another topic that I have talked to my students about it, but at this point, we don't have an answer for that.
Okay. Okay, a lot of unexplored areas still.
Yeah, that's right. You can say that, yes. I have a question from Yusuf. It says, in the case of regular reflection, we know the splitting ratio of the power depends on the polarization of the incident beam. Oh yeah, that's right.
Yeah,
it's the same thing.
Question.
Yeah, the same question. That is, I answered that. Yeah. Okay, so now I have a question from Abdullah. He says that a question about the space-time duality concept. Can you elaborate on the reversibility? So when we are talking about time and different application time lengths, when do we have a space reversibility? Okay. Space reversibility. No, it is space reversibility is so let me understand this a little bit. So first of all, there are two ways I can think of reversibility. One reversibility is that I can take the ideas from space, apply them in the time, right? That's what I was doing that. Now you can go backward. You can take ideas from time domain, apply in the space domain. So we may be able to, people in the future might take ideas which have been explored in the time domain and then get the spatial version of those. So there's a space-time itself is reversibility in the which way you go. Whether you go space to time or time to space, that's a totally reversible, I think, in that sense. The second question is, when do we have space reversibility? So let me think about that. So I think here the only thing they're saying in time, I can get a reverse in time. So like in space, you get a inversion of the image. If you do imaging, your image is inverted. We know that sometimes that. So that's just from the center optical axis, your image gets inverted. That happens in space. So in time, we can reverse the temporal profile, and that will be like a inversion in space, will be inversion in time by simply taking a mirror image of the pulse shape. So that certainly is possible. Now, space reversibility, I'm not sure what is meant by that here. When do we have space reversibility? I don't know what it meant by that. I don't know that part. But I know that we can think of a inverted image in space and inverted temporal pulse in time. They have a connection together.
Okay. Okay, quite a few questions and good participation too. So looks like there isn't any other questions. So, and we are over time. I'd like to thank again very much to Professor Agrawal for his time and for this wonderful discussion, and it gave us a lot of questions in our mind to keep exploring this very interesting phenomena. So thank you again, Professor Agrawal.
Yeah, thank you very much. I mean, I enjoyed it, and I will maybe see you sometime after this pandemic is over. Maybe we'll have a chance to see each other. But thank you for inviting me. It was a pleasure to have you.
Thank you very much.
Yeah.
Okay. So the seminar is ended. Thank you all for participating, and we'll see you next week.
All right. So let me just stop sharing, I guess. Okay.
All right, I'll just end the meeting. Thank you very much.
All right. Very good.
Bye-bye.
Bye.
Bye.